Hello, dear online learners, and welcome to the Lesson B YouTube channel. Today, we are going to dive into series circuits and parallel circuits and really get a handle on resistance. So let's kick things off with a classic mystery. You've probably seen this happen, right? You pull out an old string of holiday lights, one bulb is burnt out, and boom, the entire string is dead. Why does that happen? Well, this explainer is going to solve that puzzle for you, and trust me, the answer is way simpler than you might think. So here's our game plan. First, we'll cover the absolute basic rules of how circuits work. Then we'll look at the two main flavors, series circuits and parallel circuits. After that, we're going to put them head to head in a little showdown. And finally, we'll see how this all connects to the real world around you. Okay, let's get right into it. Part 1, the basic rules. Before we can understand the different types of circuits, we've got to learn to speak the language of electricity. First up, we have electric current, which we usually just write as the letter I. All it is really is the flow of electric charge. The best way to picture it? Imagine water flowing through a pipe. The more water moving past a point each second, the higher the current. Simple as that. But what makes that current flow in the first place? Well, that's voltage, or V. Voltage is the push, the electrical pressure that gets the charges moving. In our water pipe analogy, voltage is the water pressure. The higher the pressure, the more forcefully the water, or in our case, the current, is going to flow. And finally, there's the third piece of the puzzle, resistance, R. Resistance is basically anything that gets in the way of the current and slows it down. Imagine a narrow, pinched section in that water pipe. It's going to restrict the flow, right? That's exactly what resistance does. Every light bulb, every motor, everything has some resistance. Now, here's the cool part. These three things, current, voltage, and resistance, are all tied together by one simple, elegant master rule, Ohm's law. The formula is just I equals V divided by R. So what does that mean? It means if you crank up the voltage, the push, you get more current. But if you increase the resistance, the bottleneck, the current goes down. This little formula is the key to understanding, well, pretty much everything we're about to talk about. Okay, with those basics under our belt, let's actually build our first type of circuit. On to section 2, series circuits. This is where electricity gets only one road to travel. Just take a look at this diagram. In a series circuit, all the parts are connected one after another, end to end, forming a single, unbroken loop. It's like a one-way street with no turnoffs. This is the single most important feature. The electricity has only one path it can possibly follow. And because there's only one path, that leads us to the golden rule of series circuits. The current is exactly the same everywhere in the loop. The amount of flow that goes through the first component is the exact same amount of flow that goes to the second and the third, and so on. It never changes, it's constant. So what about the total resistance? Well, this part is super easy. You just add them all up. The total resistance is just R1 plus R2 plus R3, and so on. So say you've got 3 resistors lined up, maybe 5 ohms, 10 ohms, and 15 ohms. The total resistance for the whole circuit is just 5 plus 10 plus 15, which is 30 ohms. See? Every time you add another thing in series, the total resistance just keeps going up. All right, let's switch gears and see what happens when we give electricity some options. Section 3, parallel circuits. Now, look at this setup. It's totally different, right? In a parallel circuit, the components are arranged in separate branches. You can see how the main current comes along, hits a fork in the road, and splits up to go down multiple paths at the same time. Then, on the other side, it all joins back together. And this is where things get flipped on their head. Here's the golden rule for parallel circuits. The current might split, but the voltage across each of those separate branches is exactly the same. That electrical push is identical for every single path. This is the complete opposite of what we saw with series circuits. Now, calculating the total resistance here, it's a bit of a strange formula, but it leads to a really fascinating result. Let's say we have two 10-ohm resistors in parallel. The formula is 1 over the total resistance equals 1 over 10 plus 1 over 10. That works out to 2 over 10. But hold on, that's 1 over R total. So to get the actual answer, you have to flip it upside down, which gives you 10 over 2, or just 5 ohms. Now think about that for a second. We added a second resistor, but the total resistance went down. It was cut in half. How is that possible? Well, you've opened up more lanes for the traffic to flow, making it easier for the overall current to get through. Okay, so we've met the two contenders. Now it's time for the ultimate showdown. Section 4, series versus parallel. Let's put them side by side so their differences are crystal clear. This table just lays it all out perfectly. Let's walk through it. In a series circuit, you've got that single path, so the current is the same everywhere. But in parallel, it splits. Now look at voltage. The roles are totally flipped. In series, the voltage gets divided up among the components, but in parallel, it's the same for every branch. And what about total resistance? Adding more stuff in series makes it go up. Adding more stuff in parallel makes it go down. There really are fundamentally opposite ways of wiring things. So you might be asking, why does any of this matter? Well, let's get to Section 5, circuits in your world. Because the devices you use every single day are almost never purely one or the other. The truth is, most electronic circuits are what we call combination circuits. They're these messy, complex puzzles with some parts in series and other parts in parallel, all mixed together. What you're looking at here is how an engineer takes a really complicated circuit and breaks it down, piece by piece, to figure out how it works. This is how everything from your phone to your TV is designed. So how do they actually solve these complex puzzles? They use something called a reduction method. It's pretty cool. You just look for the simple bits, maybe a few resistors that are clearly in series or a couple branches that are clearly in parallel. You calculate their combined resistance, and then you basically redraw the circuit with that part simplified. You just keep repeating that process over and over until the whole complicated mess is reduced down to one simple problem you can solve. So let's just do a super quick recap. If you remember anything, remember this. Series, one path, the current is constant, and resistances just add up. Parallel, many paths, the voltage is constant, and adding more paths actually lowers the total resistance. And the one rule to rule them all is Ohm's law. And that brings us right back to where we started, those old holiday lights. They were wired in series, one single path. So if one bulb goes out, the filament breaks, and that single path is broken. The current stops flowing for everything, and the whole string goes dark. Of course, modern lights are wired in parallel, so if one bulb dies, the other paths are fine and the rest stay lit. Pretty neat, huh? So think about it. What other things can you explain with this idea of one path versus many paths? If you have any questions, write them in the comment section. And hey, don't forget to subscribe to our channel.